I'm going to discuss in this video an experiment called Young's double slit experiment and some interference patterns that are seen as a result. So remember that the properties of a wave are reflection, transmission and refraction, interference, superposition, diffraction. So we've already discussed reflection and refraction. And in this video I'm actually going to discuss interference and a little bit of diffraction. So there were experiments going on during the early 1900s and late 1800s in order to prove that light was a wave. So one of those experiments was Young's double slit experiment. And it actually showed constructive and destructive interference of light waves. So recall that constructive interference is when wave amplitudes add together, and destructive is when they subtract from one another. Okay, so Young's double slit experiment was to prove that light is a wave, and the wave properties that it demonstrates are both diffraction and interference. And so how the experiment was set up is that you had a light source, okay, and it was filtered by using a screen that had one slit. So you had sort of one uniform light ray that was coming through this, okay. And then you had another screen that had two slits, and then these slits would then cause the light to diffract as it moved through these slits, and the light would then arrive at some screen over here, and we would see what are called minimum and maximum points. The maximum points are places where we are observing constructive interference. The minimum points are where we're seeing destructive interference. So in terms of the constructive interference, that's where the light is arriving in phase, or the amplitudes are adding. So you'd actually see a bright spot. And then the minimum is where they're arriving out of phase, or they are canceling, and so you see a dark band. Okay? So from the light, or from the slits, these two light waves come in, and you're going to end up with what is called fringes. So those bright maximum fringes are constructive interference, and the dark destructive interference are the dark fringes. Okay, so let me just show you actually what this looks like. So I have a simulation here. And so I have a light source, and it's sending out a uniform light. And I've got two slits here, and the light is being diffracted, and then you see over here, this is what we would see on the screen. We'd see fringes of bright and dark patches. So where you see the bright fringes, that's where constructive interference is happening, and where you see the dark bands, that is where destructive interference is occurring. Okay, so if you look here, okay, this shows the constructive interference. So we can just imagine one light wave coming through, and because this light wave is from the same color light and it has the same distance to travel as the light wave coming from here, they're going to arrive in phase, or the same point in each wave is going to arrive together, so they will then add together and we have a bright area. So you have complete constructive interference at this point because of how far these light waves have to travel. In the second band over here, so we're going to see another band here, and we would see another band up here, another bright area. So if you look here, in this case, we have constructive interference. So why is there constructive interference? The reason is that the light wave that is traveling from here to here has to go one wavelength further than this one. So they still arrive in phase. This one just arrives a wavelength ahead of this one, but they arrive in phase, and therefore you see a bright fringe. Okay, then you can imagine there would be another fringe down here where this would have to move two wavelengths exactly further. Okay, and so we'd see another bright fringe. Now the destructive interference patterns we see when one wavelength is moving half a wavelength further, right? So they're going to arrive here out of phase. So this S1 is traveling one half of a wavelength further than here. So his crest arrives when this one's trough arrives, and they completely cancel out, and we have a dark interference pattern or a dark fringe. So we have equations for the interference patterns, okay? And in order to calculate them, we have to have two different equations, one for the bright fringes and one for the dark fringes. So if you look here, this shows another sort of diagram of the scenario. You have S1, the slit 1, and you've got a ray coming here, and then you have slit 2, a ray coming here. And so in order to calculate what is happening here, we actually relate the wavelength of light is being affected, because that's going to relate to how far it has to travel. M is the order number. The order number is what maximum fringe are we seeing? Are we seeing the first maximum fringe or the second or the third? Okay, and that is the order number. It's an integer. And then over here, we've got d sine of theta. D is the distance between slits 1 and slit 2. And then the angle at which it is refracted is the, we take the sine of that angle. So the distance times the sine of the angle is equal to m times the wavelength. And that's how we can determine the location that our bright fringes will appear. Okay. Now if we want to talk about our dark fringes, this is where the destructive interference is happening. So remember that instead of being in phase, as we saw up here where we had the bright fringe, and we have some factor of the wavelength, so 1 times the wavelength, or 2 times the wavelength, or 3 times the wavelength. In the case of the dark fringe, this is where the destructive interference is occurring. So you're going to have 1/2 a step off. So we still have d sine of theta to the dark fringe is equal to m plus 1/2 times the wavelength. So again, m is the order number. Are we looking at the first fringe or the second fringe? And then we add a half to it to compensate for that wavelength arriving 1/2 or of the phase